Hey everybody, it's Miss Dr. B. It is time for us to talk about molecular polarity. So I'm going to try to get this done as quickly as possible so that we can move to the stuff you got to get done in class today. So we are talking about molecular polarity. A lot of this is going to be purely review, so I'm not going to spend lots of time with it, but we'll take the time to cover at least the things that are new to you. Alright, so let me come back. I don't know why I did that. You should remember the definition of electronegativity. It should not be something that we're worried about. You know, there's electronegativity, there's electron affinity, and there is ionization energy. Electronegativity is, of course, what happens in the ability of an atom to pull on electrons that are being shared in a covalent bond. That's the one we're worried about right this very second. All right, there will be critical thinking questions embedded within the PowerPoint, whether you're listening to me or whether you are watching it. I'm going to move ahead. You need to pause the video at this point anytime you see critical thinking and go ahead and answer all the questions. It is material which you should feel fairly comfortable with, and I would like to make sure that you are continuing to think about answers in a critical thinking manner. Alright, so we've already talked about polar covalent bonding. We know that occurs when one atom in the bond has a large enough difference in its electronegativity than the other one. That's the one that will pull, that's the atom that will pull on the electrons with greater force. And it results in one atom appearing to have lost its electron. In the upper right hand corner you'll see the one polar bear. Looks like it doesn't have any electrons, whereas the guy over on the right looks like he's got both electrons. It's not real, it's not a permanent situation, but it does make interesting, it's like the tug of war down at the bottom. It makes for an interesting type of a molecule, and these molecules are referred to as polar molecules, right? The opposite of that would be the nonpolar. This is when the bonds or the electrons within a covalent bond are shared equally. The ones that are the very, very best at this are going to be your diatomic elements, your Brinkelhoff, bromine, hydrogen, oxygen. You'll see those listed down in the lower right-hand corner. In those particular cases, that's a pure covalent, and if you kind of bring your eyes over here to the right, you will see this graphic here at the bottom. This is what you used earlier in the year to distinguish between polar covalent, nonpolar covalent, and ionic. Again, polar covalent compounds are going to be right in here between the 0 and the 0.4. Between 0.4 and 1.7 is going to be, I should have said nonpolar. These are going to be your polars, right? And so these are the two areas that we're really focusing on right now, and when we're looking at covalent compounds. All right, so how does this all work? You will see on both sides of the screen, you will see periodic table of elements with electronegativities. Nobody has a larger electronegativity than fluorine, followed by oxygen, chlorine, and nitrogen. All of them being in this upper corner right over here in the dark pink that you see on the other graph. You'll see the lower numbers, of course, are on the opposite end on the lower left-hand side. All right, so how are we using electronegativity? Again, this should be review. We've done multiple worksheets with this. But the idea is that the difference in electronegativity between two elements, for example, fluorine is a 4.0 and oxygen is a 3.5. The difference between the two of those is only a 0.5. So based on this graphic, it's just ever so slightly over the 0.4. So yes, it's a polar covalent compound, but not nearly as much as, say, fluorine would be with silicon or even boron, with fluorine being a 4 and the boron being a 2.0. That actually pulls itself almost up to the ionic aspect of this. So the idea is we're going to classify, it's a predictive value, it is not 100% accurate, but that's what we're going to be doing today in class. All right, additional critical thinking questions. We just kind of went over those very quickly. Make sure you stop and actually indicate whether those bonds in the middle, A through E, are polar covalent or non-polar covalent just by taking the difference in electronegativity of the materials that are listed, carbon and phosphorus, etc. And then the 4 most electronegative. All you gotta do is look at a periodic table to figure that out. All right. So we never really spent a whole lot of time talking about polar and non-polar covalent bonds when we actually look at the electron distribution. So if you just look at this picture on the right and take a couple minutes to do this, you'll see a non-polar covalent bond. The electrons are distributed very nicely through the entire oval shape. And again, that might be the Venn diagram shape, where you have 2 different bonds or elements overlapping, and these would be electrons where they're shared. If you look at polar covalent, you'll see that the distribution is kind of leaning to the right, and that would be the element that has the larger electronegativity, and the one on the right would be, or left would be, the one that has the lower. And so it becomes slightly positive, looks like it's lost of electrons, and the one on the right looks like it has gained electrons. Then compare that to the ionic bond, where we know we have had the metals have lost an electron, the nonmetals have gained electrons, and then they are then attracted to each other through electrostatic attraction. You will not, as it says at the bottom, have a polar ionic bond. Ionic bonds are ionic. All right. So as we move forward, what we're going to be doing is we're going to be predicting molecular polarity. Now this is going to be today in class, and then remember, we're going to do a lab, and then we're going to come back looking at this in a week from now. But we'll be talking about it. We're just not going to be focusing on molecular polarity and predicting, just because I really want to make sure we get this lab in before we take a test next week, or a lab in. Okay, so you start with a correctly drawn Lewis structure. You've already done that. You have 36 different molecules which you have done. So you are going to predict molecular polarity on those 36 molecules. How do you do it? Well, you use your Lewis structures. You have a periodic table such as this one, or the one you've been given that shows electronegativities. You're going to collect the electronegativities for the elements that you're looking at their bonds, and then you're going to get the difference between them, subtracting the smallest from the largest. You'll then compare your electronegativity down to the bottom in this graphic, and then you will predict the bond type. You're going to identify your bonds for every molecule, every bond, as being polar or non-polar. Now, I'm going to go ahead and tell you, if you had 4 hydrogens, you only have to do it once, but you would know that all hydrogen to the central atom bond electronegativities are going to be the same, and so each and every one of them would have the same identification. Right, so let's just kind of do this one really fast. I'm going to actually write down over here my little whiteboard, and we're going to do this. I'm going to leave this there. We have CH2O, we have Lewis structure. You can see that in the upper right-hand corner. And so what we want to do is we want to be able to determine the electronegativity for difference in electronegativity between carbon and oxygen. Let me move this over. Carbon and oxygen, and I also need to do for carbon and hydrogen. Now I know I have 2 different bonds that are carbon and hydrogen. Carbon is, if we look at this, or oxygen, when we look at this number, is a 3.5. And carbon, when we round it, and we can round this because sometimes you only use 2 decimals at a 2.5. So 3.5 minus 2.5 means it's a 1. Carbon is still 2.5 here. Hydrogen is 2.2, which is right there. So we have a 0.3. So what that does, when we look down here, a 1 falls between the 4 and the 1.7. So this would be a polar covalent. I'm just going to write PC, whereas carbon and hydrogen is a non-polar covalent bond. Right? So that's just the quick and easy aspects of how this works. Turn that off so that you can see it better, a little bit better. And that's what you're going to do for every molecule that you've already done for me. Okay. That's not where we finish, though. All right, that's all you're going to have to do today. We still need to finish up what we're going to be talking about, though. So the idea is all molecules will fall into one of two, all covalent molecules will fall into one of two categories. Either the molecule will have no polar bonds or the molecule will have at least one. If it falls into the first category, it's real easy to use because if you will read below it, what it says is if there are no polar bonds, the entire molecule has to be nonpolar. So if the only bond we had was a CH bond, like in methane, CH4, you have 4 of these, and each and every one of those would have the same exact value, and so the entire molecule is nonpolar. If, however, like the one we are looking at, which is a CH2O, what you're going to find is that, pull that out a little bit, is that you have one that is polar. This is a polar. This one becomes a negative. This one becomes a positive. These others aren't. And so that changes how we're going to look at this. Okay, so this is how you're going to proceed. You've already drawn your Lewis structures. And you have determined, or you will be determining today, if the bonds are polar. Let's just say you said yes, like we're doing for this particular structure that we have here on the left. The next step is to decide if the polar bonds are going to cancel each other out. The only time that happens is if the molecule is symmetrical. So I got to spend just a couple minutes. I don't want to spend much time making sure we're on the same page with regard to the word symmetrical. All right, so what does it mean? I'm going to do some dogs first, and we're just going to kind of make sure we understand. Symmetry means that you could take any picture, you could take any molecule, and you could pretty much draw a line down the middle of it, and it would be a mirror image. It's one type of symmetry on either side. For example, look at the dog face in the upper right hand corner. If you take that line straight down the middle between the eyes and over the nose, it's a symmetrical shape. Why? Because you have an ear and an eye on both sides, and it looks very, very similar. Okay, that's symmetry. If, however, you drew the line horizontally between the eyes and the nose, it would be asymmetrical. Why? Because guess what? There are not ears on the bottom. If you draw that line there, you're not going to find eyes on the bottom either, or a nose on the top. So if you don't have a mirror image across that line, it's the easiest way to do it. There's other types, but you would say that this object is not symmetrical. Finally, when you look at this other picture, you'd actually look at the dog's head. It's asymmetrical from front to back. Why? Because the nose only sticks out on one side. There's not a nose on the back of the dog's head as well. So, symmetry, mirror images, same on both sides. When you split it in half, asymmetry says that's not the case. All right, so guys, I'm going to stop the video now, and we'll pick this up, and we'll have a different video in a little while. What I need you to be able to look at is this very last slide, and know that this is where we're headed. I will get into more detail later, but I don't want this to be 25 minutes. So what I want you to be able to know is that when we are talking about symmetrical versus asymmetry, and we talk about the dog, or we do anything like that, we just need to be able to understand there's two words, symmetry and asymmetry. We're going to be using both. You are going to be assessing molecules themselves by looking just like the dog, if you can divide them from left to right, top to bottom, forward to back. And if you can, they're symmetrical, and if you can't, they are asymmetry. For today, what I need you to be able to do is I need you to be able to determine whether or not bonds are polar. Right? And you're going to use electronegativities in a periodic table, and you're going to be using the graphic that looks like that to be able to, or looks, that graphic that we were talking about earlier. Okay? All right. So I'm going to stop it here, and I will see you when I get back. All right? Thank you, guys. Bye-bye.